Okay, guys, we're gonna get started now. Are you ready, guys? Okay, lab 3 is gonna be about finite state machines. So we're gonna have 3 parts. The first part is just a FSM recap because I know you did it last semester. Second part is gonna be the lab task, and the third is gonna be Ziha introducing the coursework, task 3 of the coursework. Okay, so a finite state machine again is a system with a fixed set of possible states that moves based on inputs. The next state is based on current states and input. So basically, guys, the CPU is an FSM. So this is really important for the coursework. You can basically reuse what you learn in this lab directly on the coursework, especially on task 3 of the coursework. So an FSM diagram shows every situation the system can be in and every path between them. I'm sure you guys have seen this before and drawn the diagrams and everything. So today we're gonna apply the diagrams to code. So every FSM has 5 elements: states, inputs, outputs, transition rule, and output rule. Every situation, so the states is every situation the system can be in. Inputs is the external signals. Outputs is the system communication to the outside world. And transition rule is the most important. So for every state and input, it's your next step. And the output rule is for every state, what you output. So for each FSM, you have 3 separate parts: next state logic, state register, and output logic. This is really important. Basically, every FSM you're going to design in your life is going to have these 3 parts. So this is what it looks like. This is from logic circuit design from last semester. So at the beginning of the clock cycle, the next state is latched onto the state register. Okay, so FSMs consist of 2 types of circuits. The first is a sequential circuit, which means the output depends on the current input and its history, which is the state. Sequential circuits have memory, which is stored in flip-flops, and they are clocked, so they only change on a clock edge. And the second type is a combinational circuit, so output only depends on the current input, and there's no clock and no memory. So for every FSM, you're going to have 1 sequential circuit and 2 combinational circuits. So basically, the sequential circuit is going to be the state register, and the combinational circuits are going to be the next state logic and your output logic. Okay, that was just a quick background. This is the actual FSM we're going to build today. So you're going to detect the bit pattern 1011 in a serial bit stream. So you're going to have your inputs presented 1 at a time. And when you detect 1011, you're going to output a match, which is match equals 1, basically. We're also going to do overlap detection. So that means whenever you detect a 1011, you output a match. It doesn't have to be, so you can share the bits between 2 sequences. This is the FSM diagram I drew for this FSM. So this is what we're going to actually implement in code. And we're going to test it. And then on the board, you can do all of these cases and make sure it matches. Okay, so the bits are left aligned as they build up. So basically, the first input is going to be just 1 bit, and then the second is going to be 2, and so on. So when you get 1011, you output a match. Otherwise, you output 0. Yeah, basically, this table also includes it includes the history and the hex history. So basically, it's the hexadecimal value of the bits so far. So 1011 is equal to 11, which is B in hex. This is going to be outputted in the FPGA, so you can double check your history and keep track of what's in the registers at each time by kind of looking at the hex values. So there's also an incorrect sequence there for you to look at. So obviously the match is always going to be hex value B. Anything else will not give a match. Okay, so we're gonna obviously implement this on the FPGA. So these are your inputs. Obviously, you're gonna have a clock. Every FSM needs a clock. And then switch 0, which is the furthest most on the right, is gonna be D in. So that determines the value of the input bit. So if it's switched on, it's gonna be 1. If it's switched off, it's gonna be 0. And then button C, which is the middle button and the little plus button thing on the FPGA. Button C, the middle one, is going to be a reset. So it's going to take you back to state 0. So wherever you are in this diagram, if you press the middle button, you're going to go back to state 0. And then button U, which is the upper button, is going to take you one step forward. So again, if we go back, let's say you're in state 0, you flip the switch to 1, and then you press the upper button, you go to S1. These are your outputs. So I didn't mark them on the diagram, but you're going to have LED 0, 1, 2, and 3. LED 0 is going to light up when you match the sequence. LED 1 is the state bit 0. LED 2 is state bit 1, and LED 3 is state bit 2. And the 7-segment display, obviously the 7-segment display has 4 digits. So the rightmost digit is going to have the 4-bit history as hex, as we spoke about here. So it's going to have the hex value of the history. The yellow one, so the middle right one, is going to have the current state. So which states you're in this diagram. It's going to have 0, 1, 2, 3, or 4. Obviously, it's going to be 4 when you match, and that's what the green one is for. Basically, it tells you if you're matching or not. And this is just to see if you have any errors. So if green is 1, yellow has to be 4, basically. These are the files for the FSM. I've already given you all the code, so you just have to run it and implement it on the FPGA and see if you find any errors. So of course, the most important one is sequence detection. So that's the FSM itself. Has 5 states. So each state is one of these. So 0, 1, 2, 3, 4. It has a next state logic and output logic. And then I also put a button debouncer because the buttons don't really work well if you don't use debouncing, especially if you're gonna use buttons on the coursework. I recommend you do debouncing just so it doesn't like bug out and you don't know what's causing the issues. 7-segment display obviously is gonna output the digits on the 7-segment display. Top again is the top level wiring. So you're gonna connect everything together, all the inputs, outputs, and the actual logic from the FSM. And then I also included a test bench, so you can check the simulation before you run it on an FPGA, which is what we're gonna do next before actually running it. And then I included the constraint files as well, so you don't have to manually kind of put the inputs and outputs and everything. Okay, again, this is the template. So you are going to build an FSM for the coursework. An FSM is an important part of the CPU. So you are going to need to build one. This is the basic template. Also, you can look at the code that's provided to get an idea of how to build one. But you're going to have 3 blocks. So the first is a state register, which is sequential. So has always FF. Again, this is in system Verilog, so you're going to have always FF, which is specifically for flip-flops. Flip-flops are needed for a sequential circuit. So yeah, update states on the rising clock edge and only move to next state when step equals 1. This step is controlled by the upper button on the plus sign buttons. And then synchronous resets returns to 0. So basically, the middle button on the FPGA returns to state 0. And then block 2 is next state logic, which is a combinational circuit, one of the two combinational circuits in an FSM. So you compute where you're going next. So what's the next state? A case statement checks current state and DN, because in an FSM, the next state is always determined by the current state and your input. Again, these blocks 2 and 3 are combinational, so you don't have a clock. And then block 3 is output logic. So basically, it sets match equals 1 when state is S4, which is when you detect a sequence. And then again, this is output depends on state only, not DN. So it's just if state is S4, then you output match equals 1. Okay, we can get started with Vivado now. So you're gonna create a project just like last week or the week before. Again, just do not specify sources. Make sure you choose the correct board. You can copy this code, or you can press on boards and then select basis 3. Again, just like last week and the week before, add sources. I've already given all the code on Keats, so you just have to download and then upload them on Vivado. Don't click open project here. You have to create your own project and then copy the code files inside. So again, after you're inside your project, press add sources and then add or create design sources. Add your files. And then it's these 5 files that you want to add. Again, they are on Keats, so if you haven't downloaded them yet. Yeah, just add the files. And then in the Vivado workspace, if you stay in hierarchy and then go on simulation sources, right-click the test bench, which is sequence detect TV, and then set that as the top file. Like 30 more minutes. Okay, guys, after you've set the test bench as the top file, you can get started on the simulation. So just click run simulation and then run the behavioral simulation. You're going to get a new window untitled 1 or, well, it's depending on how many times you've run this, but click on the new window and you're going to see the waveform. So you can actually use this to double check that the state diagram that I gave is correct. You can like sort of prove the FSM. We'll come around and check how everyone is doing with the simulation before we move on to the next part. So 5 minutes and then we'll see how you're doing with this. Desktop. I plugged in USB2. Doesn't work. Used to be USB3. Yeah.
Right. So yeah,
By the way, they're asking when the April
get up the
can do yeah. Yes, Like an hour.
An
then.
hour, right?
Yeah. Are you?
No,
So like busy. I saw you were.
no, no.
Okay, guys. So after you finish with the simulation, you can run this on the FPGA and test it out. So first, just change the top file to the top.sv, and then like we did. Oh, actually, you need to add the constraints. So add sources, add constraints, and then I already gave you the file. So you just need to add this to your Vivado. The XDC, the constraints file, is the translation layer basically between all your code and the physical pins on the board. So you're basically connecting the board to your code. And then just like last week or the week before, run synthesis, then run implementation, and then generate your bitstream and upload it on the board.
We have to laugh us. I'll have a like this. The real cool. Like the last two lab sessions. No, no, no. Basically, next lab. For lab 5, we So, I like I USB and I was able to use it and ask you a question.
Yes.
Yeah, thank you so much. Yeah. What should the size of the
I will say
enough for? So much.
double check for the visor. Yes, do they understand their own security? Yes, okay. Basically, everyone have a private meeting. They do present. Okay, so I'll be in the Viva also. So then they'll be presenting their CPU demonstrating for. So we're gonna be asking questions. The Q&A session will be next. That's fine. Oh, no, no, but in the Viva, do we ask questions? Yes. Okay. We should ask some like simple questions. And on the feature. Request. Everything is yeah, we can do it. This makes this time I actually try to I'm a little bit struggling on final stage. This is custom, right? I need right. I deal with Gemini first. Gemini help me. I choose a because Gemini is not the cloud is better. True. So that's why. So the reason I start with Gemini is because I have all the I say in the table, right? And I can use Gemini doesn't. That is. Uh, I will post every code, all the codes on our GitHub. I have the file. That's all. Yeah. Oh, it's running, but it's not perfect. To give the. I am thinking about giving them to students. Why do they? why, because okay. Yeah, sure. So, yeah, you can do it. So, what do we look like?
I'm waiting for Sasha. Guys, so this is it running on an FPGA. So again, this first switch is the input. So this is what makes a 0 or 1. So if you do 1 and then press the upper button here, now you're in state 1 and the hex value is 1. So you want 1, 0. Now you're in state 2, hex value is 2. And then 1, state 3, hex value 5. And then to get to S4, which is detecting 1, 0, 1, 1, is another 1. So now your match is 1, you're in state 4, and the hex value is B, which is 1, 0, 1, 1. And then this middle button takes you back to S0 and resets everything.
All right. Is there any questions right now for the previous lab work? If no, we can have a quick cap on the coursework. Hey, I have no idea whether you know. Or should I switch the laptop? I chose computer, but this computer is close the visualizer for now. Yeah, it will be a close visualizer. It automatically comes. Oh, okay.
There we
Now
go.
it works. Okay.
Yeah.
All right, everybody, this is part 3 of our coursework. Right. So as you're making a CPU, and we have already made the data bus in task 2. And maybe you have already tried with the data bus where you have to click all the switches all the time to just make one simple calculation. It's a little bit tedious. So in a CPU, you usually have a controller, which is the FSM for the CPU. And this is what we have now after task 2. And this is the data path you have. And basically, if you recap the idea of CPU, it's basically a factory of data, and you have already finished the data path, which is the way of processing the data. Now, what you are trying to do is make the controller, which is the FSM. And for now, we have to update the data path for task 3. Previously, you have 2 inputs. Now we have 4 inputs. The 4 inputs, we have XIMM8, T, TXIMM8. We have a PC plus 1. We will not cover this in lab 3. And we still have the data path in. So in order to deal with 4 inputs, we need to make the V cell to be a 2-bit selector signal. So this is an overview of our lab 3. You can see you already have something with lab 2, right? The data path. So now you are going to add a instruction register along with the FSM. I hope you are familiar with this because this is exactly the thing that we have already covered in our lecture. And let's have a quick recap on what we have to do right now. The first thing is the instruction register. Basically, instruction register is a register that holds the fetched instruction. It is synchronized to clock, but it is updated or say enabled with a signal called load IR. IR refers to instruction register. It's a 16-bit register, which is same length as the system architecture. In the CPU, you have the controllers. One controller is called arithmetic controller. I put it just arith control here. The arithmetic controller is the same as the ALU control block in the MIPS architecture we covered in the lecture, but more simpler. Basically, it only do two things. One is pass through, which means the ALUOP is 0 and shift is 0. You just use a add instruction, let the ALU do the adds. So user can use this mode for non-arithmetic operations like jump, like load, like branch. The other one is IR mode, which is the functionality of the ALU and shifter is based on the instruction register. So ALU OP and shift OP are from the instruction. You use this mode for all the R-type instructions and I-type instructions. All right, so this is a quick cap about the supporting instructions we have to deal with right now. So in lab 3, you are going to support the following instructions. These are very simple instructions. Basically, we only covered R-type instruction, I-type instruction, and load register instruction. In lab 3, you will not cover memories. So lab 3 will let you just focus on the FSM design to have a quick idea about how to make a FSM for the CPU. Basically, FSM is used to control the data path, IR, and arithmetic control. Also, the data path out gate. I'll cover the data path out gate later. While the FSM, write FSM states to automatically control the CPU as you did in lab 2. So you need to support the following instructions, which is R-type instructions, I-type instructions, and the load register in immediate instructions. And as Ali just covered in the early part of this lecture, you are going to write the FSM in the following way, which is you have the output logic, you have the next state logic, and you have the sequential circuit, which is the status update. And in the FSM, I suggest you to make the 4 simple states as a starting point. Initially, you have an init states. This is where the state where the CPU is reset, or the first moment it is powered on. So in the init state, you just reset all the signals you can see in the CPU. And in the next state, this is a fetch state. Fetch state is pretty simple. Just keep all the other signals as default, and you enable the instruction register to load one instruction from somewhere else. And then is a decode state. Decode state is basically everything you covered in previous a single cycle CPU or multi-cycle CPU. It controls all the signals inside this CPU. However, the next stage is different because in the last task, we tried that the load instructions only need one cycle to complete, while the execution, the arithmetic execution requires 2 stages to complete. Therefore, for the load instructions, you can just go back to fetch after decode is finished. But for the arithmetic instructions, you have a write back stage. That means you have to decode the instruction based on the instruction register output. And I have provided a table here for you. It's the decode table for the decoding stage. This is the way I suggest you to write your FSM for the decode stage, which is using the case statement. In the case statement, you can write up different cases, just like C language or C++ languages. You can use the IR opcode to make different cases for the different decoding instructions. And finally, you have the execute, or saying the write back stage. The write back stage is dedicated for the R type instruction and I type instructions. Because for the write back stage, you need to write back the data path data back to the register file. So in this way, you need another stage with different control signals to allow the data is written back to the register file. In this structure, we include a tri-state buffer and a data bus. Data bus is basically, as you know, the bus for the data. Because this CPU, because the data path is shared, it's not just the data path out need to write the data path. Later, you have other peripherals like memories, like I/O that is connected to the data path. Therefore, you need a gate. Basically, it's a switch in between the data path and the data path out signal. So this tri-state buffer is basically a switch allowing the output data path out right to the data bus or not. So the way of doing it is pretty simple. You can just assign this data bus with a tri-state statement where if the gate is on, you just pass through the value. If the gate is off, you assign to 1BZ, where Z here means high impedance. High impedance basically means disconnect this signal from the other signal. Also, we have a sign extender. I have covered this in lab 1, but I just make another quick review on what is a sign extender and tail extender. Sign extender is basically you extend a lower bit number to a higher bit number while keep the sign. Because we covered in two complement numbers, the MSBs are signs. So basically for the sign extender, you just copy the MSB and fill the and fill the extended part. So the tail extender is even more simpler. It's basically uh, shifting logically shifting by left. And I have provided you some examples here so you have a better understanding what is sign extender and tail extender. In our CPU, we will have a sign extended IMM8, which is sign extend 8-bit to 16-bit. And we also have sign extended IM5, which is extend a 5-bit number to 16-bit number. Finally, we have a tail extender. The tail extender is basically shifting the 8-bit number left by 8 bits. So this is an overview of lab 3. You already have the data path ready. You just make some quick edits on the data path to support more inputs. And in the data path 3 top file, you have all these instruction registers. You have all the FSM, and you have the data path, which is implemented in task 2 already. So this is a top file that I provide you. Basically, this top file will connect to the switch as the input. So you can implement your instructions with the switch. And for the output, you have the 7-segment display to display what is on the data path. All right, so that's everything for lab 3. Now I'm going to give a quick demo about what would be an implemented CPU like on a basis 3. All right, as you can see here, we have the basis 3 with, okay, wait a second, it's not programmed. Here I provided this cheat sheet. I'll upload this cheat sheet later so we can also play with the CPU using this cheat sheet. All right, I hope it works. Now I have programmed my CPU to the basis 3. And this is how I define the switch and the clocks and the push buttons. For the push button, I only implement two push buttons. One is reset, which is the center push button, and one is clock. So you can manually control the CPU. So this is clock. If I push clock, you can see some light is on here. This is how I define the LEDs. So for the LEDs, they are defined in this way. The first one is a fetch signal, which means when this LED is on, you need to use the switch to implement your instruction. And we have a state LEDs here. I use 3 bits as the states, and I have an arrow LEDs here. If this LED is on, it means my instruction is somewhat wrong. And finally, I have all the status that is implemented as to the top file. So you can use the LEDs to debug your CPU. So now it's in a fetch state. I'm going to give it a instruction. And for the first instruction, I'm thinking about load some data to the registers. So this is my part of the cheat sheet. And you can see this is how the push buttons are mapped to the instruction. For example, I want load uh, like 16 bit 5555. I will take the push button in this way. So this intermediate data refers to a 55, and this RD means the destination register. I will just leave it to 0. And now we have the ALU OP, which is op code for the instruction. And for LDI, which is lower 8 bits, I will just leave it to be 10000. Now I'm going to use the clock to make it wrong. So you can see the state changes here, and I give another one. Okay, you see the fetch LEDs on again. That means this instruction is successfully finished, executed, and I'm going to give it another instruction. So for now, I'm thinking about maybe just load register 1, a maybe just 1. So I just click 2 times. So this execution is finished. Now I can try some arithmetics. For example, I'm going to do add R2, R1, R0. So add is, as we said before, add is 00000, and RD is register 2. So I just give it 2. I push it to 2, and RA is 1. For the shifter OP, I just leave it 0, so I don't do any shifting, and for RD, it's 0. So because now I have 055 and I have 01 add together, so the result should be 056. I'm not sure. Let's try it out. So first pushing, it goes to a decode state. But as we mentioned earlier, in the decode state is not the finish of the arithmetic instructions. So I give it another push. Now we have the data on the data bus. And you can see the result is here. Is this finished? No, because this is the state of writing back, which is a WB state. So you need another push to finish this instruction. And now you can see everything goes back to 0 again. That means the data is successfully written back to the register file, and the data bus is cleared by the data bus gate. So now I can give another try. For example, I want to execute shift left R0 to R7. So I keep the opcode to be add, and for RD, which is destination register, I give it 111, which means R7. For RA, I'm just leaving it to be R7 because R7 is 0 by now. Now for the shift OP, because I want to shift left by 1 bit, so the shift OP with 0, 1, I just gave it 0, 1 for the shift OP. So finally for RD, it's R0 because R0 contains 0 x55. So this is my instruction. This instruction is shift left by 1 bit from R0 to R7. So let's try it. Yes. The result is AA. Basically is 5 times 2. That means I shift left by 1 bit. And now I give it another push. Yeah, it goes back to 0. And you can see the fetch LED is on, meaning that this instruction is successfully executing. So now this is a quick demo of our CPU with FSM. For now, we don't have any memory implemented. All the input and outputs are from the switches and the LEDs. And you can debug your own CPU FSM, and you can play with your CPU on the basis 3. So this gives you a better understanding about how the instructions are executed in the data path. I hope you have a good feeling about this CPU FSM, and I have already uploaded the test bench on our online simulator. So when you finish, you can try them on the online simulator. You can also try it with your basis 3. So this is for the task 3. If you have any questions, you can contact to me right now. Here's some logistics updates. Ideally, I'm going to give some instructions in lab 4 and lab 5, and half of the lab 4 and lab 5 are the Q&As. But some of our students are rushing on the coursework, so I changed the plan. In lab 4, I will give all the rest of the coursework, and you can have lab 4 and lab 5 as a Q&A session if you have any question regarding to the coursework. So this is today. I hope you are fine with the coursework. You can ask me right now if any questions regarding to the coursework or the lab